So improve emulator test quality by applying the synthesizable functional coverage. So the abstract emulation significantly helps to reduce our turnaround time, and it can cover the corner cases of failure in the design, which is hard to find in the simulation. However, it is more difficult to check the design functionality comparing with the simulation. For that reason, it's needed to apply the functional coverage in emulation. Each vendors have already provided their own solution, but it's difficult to reuse coverage code used in simulation, and there are differences in the syntax supported by each emulator. In this paper, we present a common rules for writing synthesizable functional coverage models can be widely used for both simulation and emulation. Moreover, we show a benefit measuring the functional coverage through the case studies which apply in emulations. Introduction. Emulator is introduced when some issues are found with a very low probability or a huge tester turnaround time, TAT, is required because emulator is much faster than a simulator generally. However, it's difficult to confirm how much design intent had been verified for emulation based on simulation. In the simulation, the functional coverage has been used to verify the design functional intent. Functional verification also can be disclosed by adding test vectors for uncovered area. We'll refer to the experience conducted by simulation and decided to apply the functional coverage to the emulation. There are benefits when a functional coverage is used in the simulation. First, like a simulation, a percentage of functional verification progress can be checked in simulation. Second, by defining the functionality for long TAT test scenarios that are hard to finish in the simulation, a functional coverage metric data for the test scenarios can be measured and the test can be performed within a limited period. Third, by applying the functional coverage for full combination test scenario, the missing cases can be found easily, and the test vectors for the missing cases can be made quickly. Therefore, it's helpful to choose the minimum test vectors to verify for combinations. Lastly, emulation and simulation can share functional coverage code, and each coverage matrix data can be merged. Comparing with the simulator run only, it takes less time to complete verification and the coverage closure as emulator and simulator run all test scenarios together. As a result, it has the effect of reducing the test TAT. We use the C vendor and M vendor emulator. Each EDA vendor already has its own solution with its user guide document. However, it's challenging to reuse functional coverage code applied in the simulation when the coverage is implemented in the hardware due to the emulator capacity and some functional coverage syntax supported in the emulator only. In addition, there are some syntax differences between both emulators. To solve this problem, we propose common rules for writing synthesizable functional coverage models that can be implemented in less capacity and can be used both simulation and emulation. This paper helps emulator users to accelerate the functional verification and finish the verification by measuring functional coverage and adding test vectors for uncovered area. Considerations. For writing common functional coverage, we should take into the account 3 considerations. 1. Capacity. 2. Speed. And 3. Functional coverage syntax. A. Capacity. Unlike a simulation, emulators have limitations on the number of beans can be implemented due to resource constraints. C vendor emulator managed the bean count of the entire coverage data by setting the internal memory counters. Max 2,147,483,647. it's a 2 giga count. Okay, right. As the M vendor emulator cannot make more than 4,996 beans per cover point, and the total bean count is limited by the AVB board capacity. Therefore, more efficiently, we use the given capacity, more coverage. We can implement coverage in the emulator. EDA vendors are also trying to improve the emulator capacity. However, design user verification DVs also become more complex to meet the market demands. Therefore, it is always important to consider the capacity limitation when we use emulator. Next is B. B is speed. While running tests, C vendor and M vendor emulator store coverage data into memory in the background at the same time and execute coverage data dump at once after all test cases are finished. For this region, there is a very little difference in runtime depending whether the functional coverage applied or not. With 191,797 beans, the coverage data dump only takes additional 1 to 2 minutes. Table 1 shows a runtime between applying functional coverage or not. Therefore, the emulator capacity is sufficient. The emulator is more useful for measuring coverage than simulation because it is inevitable to get lower speed to run simulation with heavy functional coverage. C. Functional coverage syntax. According to C vendor and M vendor's functional coverage user guide document, there are functional coverage syntax allowed only in each emulator. Furthermore, some syntax used in RTL simulation are not synthesizable, so it cannot be an emulator. Applied in emulator. Therefore, it's not ideal to support functional coverage which a specific emulator is only supported. To overcome the difference, a common coverage design pattern is important. In section 3, we introduce a functional coverage coding guideline considered in 3 factors above. Section 3. Suggested functional coverage coding guidelines. In this section, we present common rules for a synthesizable functional coverage. 1. Bean count limitation. 2. And 3. Cross coverage. Ignore beans usage separating into cover groups. 4. Sampling. 5. Multiple instances of cover group using parameter. 6. Cover point guard. And 7. Applying set_inst_name option. A. Limit the number of beans. In case of M vendor emulator, the number of beans per one cover point must be not exceed 4,096. Therefore, a cover point with a large number of beans should be divided into multiple cover points that covers different slices. Cross coverage of those slices are equivalent to the original coverage as shown in Table 2. Table 2. Guideline for bean count limitation case. B. Resources reduction of cross coverage. Ignore_beans usage. In the case of the C vendor emulator, instead of using ignore_beans in cross coverage, it's better to apply the ignore beans at cover point, including in the cross coverage to use less emulator resources. Table 3 shows a comparison of resources between 2 cases. Even if the number of beans is reduced by using ignore_beans within the cross coverage, the emulator internal memory requires space to store all beans, which does not apply to ignore_beans. For that reason, we recommend that ignore_beans apply to the cover point instead of cross coverage. The Table 3 guideline to use minimum resources of cross coverage using ignore_beans. C. Resource reduction of cross coverage Separating cross coverage. If a cover point is included in multiple cross coverage, it's better to separate the cross coverage into different cover groups. Table 4 shows an example how to separate the cross coverage. Table 4 is guideline to use minimum resources of separating cross coverage. So in the table 4, the cover group CG_A is applied to the C vendor emulator. It's considered to cross coverage PA, PB, and PB, PC as one cross coverage PA, PB, PC, and it causes increasing the address spaces required to store the internal memory counters. It also requires more gates and can affect the emulation performance. After cross coverage PA, PB, and PB, PC are separated into different cover groups, CG_B_0, CB_B_1. So the emulator needs two small memory counters, even though a memory for a cover point PB is counted multiple times in each group, in each cover group. CG_B_0 and CB_B_1. Sampling. In the simulation, the coverage is generally sampled using the sample method. However, the sample method is not synthesizable in emulator. Instead of that, we have to define a special sample, even like a pulse edge clock. The table V shows a comparison sampling coverage between simulation and emulation. Table 4 is a sampling example in the simulation and emulation. So, to describe different sampling in the table 4, we assume two virtual data paths A, B, A and B. The verification purpose of the example is checking a combination coverage for two data paths and the cover_data_path cover group. Here it is a specification for a sampling example. CHA_SCN_data path information for A data path. CHB SCN data path information for the B data path. CHA start plus CHB start plus start parse valid signal for each data path information signal. Or_SCN_done operation for the data path is done. The two data paths are operated asynchronous, so the valid signals can be asserted at different times. In the simulation, the data path's information can be sampled when each valid signals are asserted. Once or_SCN_done signal is asserted, coverage can be measured using sample method. On the other side, because the emulators do not support the sample method, the data path information should be latched until the or_SCN_done signal is asserted. So the figure 1 illustrated a timing diagram latching data information signals in the green and the sampling time in red. And in the example, the LAT_CHA, CHA_SCN_data_path, and LAT_CHB_SCN_data path signals are used for latching, which are not necessary for simulation. In the emulator, the latch signal should be forwarded across a coverage instead of data information signals. So the cover group for emulation is defined in the sample event at pulse edge or_SCN_done to measure the coverage when the or_SCN_done signal is asserted. Figure 1 is latching and sampling in emulation. The E. Multiple instances of the instances of a cover group using parameter. In a simulation, a cover group can be defined with the argument, which is used for a cover point specific condition at IFF clause. However, the argument of the common cover group is not supported in vendor emulator. So to solve this restrict, the specific condition should use a parameter and module declaration. In table 4, we show a comparison between a using cover group argument in a simulation and using parameter in the vendor emulation. Table 6, guideline for multiple instantiate of cover group in specific condition. So according to the table 6, the block ID information is delivered through _block ID, block under ID argument when a new construct is called in the simulation. So in the other end, vendor emulator, the curve_top module is defined p_block ID parameter instead of cover group argument. So the cover point can use the block_ID information at the IFF clause like a simulation. So the emulator verification engineer wants to check the curve_data path coverage according to the p_block ID parameter. The curve_top module should be instantiated as much as the type of test value in the tb_top module. So F is cover point guard. The width clause is now synthesizable in both emulators, so the bins in cover point cannot be defined with width clause. Instead of a width clause, specific condition can be applied when a cover point is defined with the IFF clause. Table 7 shows an example which can be a cover point according to the PID in simulation and emulation. So table 7, cover point if IFF guard instead of the width clause. G, apply the set_inst_name option. When a single cover group is instantiated in multiple times, the set_inst name option is used to prevent generating the same instance name. The set_inst name should be applied in initial statement in C vendor emulator. Table 8 shows an example for applying the set_inst name option. The table 8, applying the set_inst name option. Next is section 4, reusable coding synthesized with a simulation. Unlike a syntax difference mentioned above section, there are reusable functional coverage coding style which can be applied with both emulation and simulation. In the table 9, we introduce 4 cases that are used for writing coverage based on our experience. 1. Ignore beans. 2. Define beans with an unsized array. 3. Wildcard beans. And 4. Transition bean. Section 5, Integration Functional Coverage. The UVM, Universal Verification Methodology environment, has UVC, UVM verification component, including UVM driver and monitoring scoreboard and sequencer, and DUT, degenerate test, wrapper that can be synthesizable. The functional coverage is placed in the UVC scoreboard can be declared as a member generally. However, we changed the functional coverage code place from the UVC to the DUT wrapper. Figure 2 illustrates a block diagram of integrating synthesizer functional coverage block, and table 4 shows simple examples of implementation in both class and module. Figure 2 is the integration of synthesizer functional coverage model. So the table 10, simple example of implementation in a class and in a module. So the functional coverage module data path and curve, data path underscore data underscore path underscore curve is wrote in a module, not a class. It's written in a module but not a class. Okay, right? The interface modules curve underscore inf that are defined. The internal blocks interfaces are used for connection between functional coverage module and DOT's internal signals. The functional coverage module is green, can be instantiated in the simulation without a modification, and can be applied to C vendor and M vendor emulators. Furthermore, a conventional verification environment that even is not generated as UVM can reuse the functional coverage module. If the functional coverage code is a part of UVC instead of DUT wrapper in the emulation verification, it might cause a negatively performance impact by having to pull signals from the DUT to correct coverage. This is why we selected the DUT wrapper for integration in the emulation. The section 6, merge the coverage matrix data. If emulation and simulation use the same functional coverage code, the coverage metric can be merged using the related vendors to merge tool or script. But for merge the coverage matrix data, you have to check below. Each emulator's coverage data can be merged with each vendor's simulator's coverage data. And a block hierarchy including the functional coverage in the emulation should be same with the simulation. It's a common case to use different emulator comparing with the simulator because each emulator has advantage for a special use case. However, it's hard to manage verification progress and field coverage holes when we use different vendor simulator and emulator. Therefore, it should be better if the coverage matrix data between the different vendors can be merged. The Unified Coverage Interoperable Standard UCIS provides an application programming interface API that enables the sharing of the coverage data across software, hardware, accelerators, formal tools, or custom verification tools. We are gonna try to merge the emulator's coverage matrix data with the simulator's data generated by different vendors using UCIS for the next step. Section 7, Case Studies. Two best practices are presented to show the benefit of the measuring functional coverage in emulations. A. TAT reduction of corner case hunting, and we define the functional coverage with 2,632 bins, including the corner cases that can occur with a low probability. We perform all test scenarios with the emulator in 2 weeks. However, with simulation, it might took several months because each test case consumed several hours or days and needed hundreds of frames to finish a test. In the table 11, we compare the test TAT between the simulation and emulation. Table 11, comparing TAT for corner case hunting. And B, measure full combination coverage. By defining full combination as a functional coverage with 4,846 bins and verifying in the emulator, we were able to verify all combinations without omission cases, and also found the bug is that only found in a specific combination in the actual project. Without a functional coverage, it was difficult to know whether the probabilistic combination was verified or not, even though many tests were performed repeatedly in the emulator because test vectors for full combination scenario has been generated randomly. Section 8 is conclusion. In this paper, we propose the common functional coverage coding guidelines in 7 cases to improve emulation test quality and applied in applied it in C vendor and M vendor emulator. We discussed the integration of functional coverage module and coverage metric data merge. With two case studies, we showed effectiveness for TAT reduction and sustainability for full combination coverage. Okay, today I read this paper from the DVCON2023. So thank you for your time and see you next time.